Hello, everybody. This is going to be a quick demo on X10, specifically a feature in X10 called Finish, which would join all of the tasks you created within its block. And so really quickly, X10 was a system out of IBM research that was a programming language focused on parallel programming, and nicely won most influential paper for OOPSLA, which is the programming languages conference in the ACM. And so it's nice to win best paper. It's even better to win most influential paper 10 years later. 2015, they won the award for this. And that's because it interests a lot of interesting things in parallel. One thing I want to talk about right now is called Finish. And so this is a quick Rosetta Stone between some of the language you might hear in fork join versus X10. There's just different terms, different libraries use different things. So what we call fork, they call future. What we call void fork, that's something that didn't return, a task that didn't return anything, they called async. They had, both have parallel for loops. We call it the void fork loop, what they call the for async loop. And there was a lot of sort of emphasis on this, async and for async, sort of things that don't return anything. We'll talk about that in a minute. Whereas we have join, they had this construct called finish. And really quickly, there's a more complete version of this Rosetta Stone between fork join, X10, threads, executor services, and Silk on our wiki, just for you to check out. Now, importantly, the semantics of this finish from X10 was it would join, like I was saying, all tasks forked within its block, period. So if you called a function from the block, it would, and you forked any task at all within it, it would join it. You could do it recursively and call them. You could put one of these for async loops in there. It would join them. So any and all calls at all. So you didn't have to capture the future and join it explicitly. And so really quickly, let's go over an example here. I have the classic hypotenuse. I've torqued it a little bit to work like X10, where we're going to mutate this array outside. No big deal. I have this void fork that's going to compute a squared, right, in parallel with computing b squared. I join it up in our fork join style, and then square root the two array slots. Over here, I do sort of the same thing. I just launch one of these. We're going to call it a void finish because we're not going to return anything. Again, they called it finish, and by default it didn't do void, but we're going to stay consistent with our void tagging on. They would do this finish and wrap everything in here, and everything that you create, there was only one task we would create, only would end up being joined before this block finished, right? And so here we have the same void fork we have over here. We don't have to catch the future because we don't have to join it. Void finish will join it for us. And then again, we compute in the continuation this b squared, get the same answer. You look at the computation graphs, you can see how they're equally parallel. It's a little bit, there's this beginning and end, the enter and leaving of the finish right here. It's not all that inspiring from a computation graph, or for this example. If I come over here and sort of run this hypotenuse demo, you can sort of see both versions, both of them computing the correct answer. They're both computing for 3 and 4, 5. So it's pretty equivalent, right? In this regards. Where it gets more interesting is when you do something crazy like this. So this is kind of like trying to print like crazy. Let's just call it. We're just going to start a bunch of tasks, all of which print, and nobody is catching a future and nobody's joining anything, right? So in this thing, I imagine the main wrapping these two, joinless printing. Let's just fork a task to print A, fork a task to print B. We're going to make a fork loop, a void fork loop. It's not going to be a join one. We're just going to launch Fred, George, and Ron. They're going to print. Then I can do this divide and conquer joinless printing, where I go and do all that. And if I sort of the computation graph for this is like this. It's just like constantly forking tasks. The continuation continues all the way down. And I want to do this thing where I want to print last word, and all these guys are sort of printing in any order that they want. And so when I run this, so to say, turns out A, B, they happen here, like these happen in order. It's not sort of guaranteed to do the same print every time, like I just sort of print differently. The critical part is imagine, like at some point I want all of these things to stop, right? And so, like I don't want things to just run in any arbitrary order. I want them to, eventually complete. And so I built a quick implementation of a small portion of X10. That's going to be the the fork join X10, right? And if you have an instance of one of these, you can just say X10.finish. You can say finish. That's the one that returns something. Let's just do void finish, because that's we're not returning anything right now. Void finish. And I can make it a block. Make sure that everything above it, which obviously can still run in parallel because we're creating tasks, but it makes it so all of the tasks that are ever created will always join before I exit this block. So I can make sure that the same way we would make data races before, right? Like, or prevent them, right? Like, it was used in the same way here. It just was less exciting because there was only one task, and we could have grabbed the future just as well than called join. In this case, same sort of thing. Like, before I do the square root on this array slot sub 0, right? I don't want to have a data race here. Let's join everybody within. This guy will do the same thing, but in a more aggressive way, where like we've got tasks being created in a separate method within a for loop within divide and conquer. And so if you look at the sort of new one that has this part where I'm finishing up join list printing, all the tasks that it ever creates, from whether it's a fork loop or from divide and conquer or whatever, and brings them all together. And now what happens is, you can imagine sort of the beginning or the entering of that finish block. Up here, calls join list printing, you get the same computation graph where everyone's making tasks, but X10 is keeping track of all the tasks that you make so that it can join them all up to sort of you can imagine a leave node before it prints out that last word. And so we, if you look at this example, this is a pretty contrived example, right? Like, I'm just printing stuff like crazy and not capturing anything. We're going to use this feature of finishing and joining all the tasks within in non-contrived ways in this class. And hopefully this video will help.